Hello, and thank you for joining us today for our webinar, WaveFarer Radar Analysis with Diffuse Scattering and Backscatter Through Walls. I'm Greg Skidmore, the Director of Propagation Software Modeling Tools at Remcom. In today's webinar, I will demonstrate some of the capabilities and new features in WaveFarer, Remcom's radar simulation software tool, and I'm going to apply them to two application examples, including an automotive radar drive scenario and an indoor millimeter wave sensor scenario. My hope is that through this talk, I can convey some concepts and ideas on how modeling and simulation can help solve some challenging problems in the many growing fields where the industry is using radar. So the focus of today's webinar is on an overview of new features and capabilities, and we're going to do this by going through a couple of examples. So our first is a drive scenario at an intersection that we have set up, and our second is an indoor radar scenario that's emulating a scenario that uses an indoor millimeter wave radar sensor for people counting and tracking in an office. Wavefarer's new features improve support for radar applications. Some of the key new features include diffuse scattering, which captures backscatter from rough roads, buildings, and terrain, transmissions that can penetrate through walls, windows, and furniture, and chirp simulation scripts and post-processing that generate range-Doppler outputs. Some of the key takeaways include learning how some of these features and capabilities, both the existing capabilities and the recently added ones, help it handle a wide range of indoor and outdoor radar applications. And some examples include the diffuse scattering to model clutter, combining transmission through walls with multipath diffraction and backscatter to evaluate returns in an indoor scenario, using chirp simulation scripts and post-processing utilities to simplify both the setup and to allow you to perform range-Doppler analysis with the results from simulations. And then we also have a few new features that include enhancements for how we can model materials that have significantly expanded the types of materials that we can handle and the ways that they can be defined to help simplify how they can be used over a broad set of frequency ranges. Before we get further, I just wanted to make sure everyone was aware that during the webinar, you can ask questions by entering them in the dialog shown here. And you can optionally undock this. Sometimes that makes it a little easier to type in your questions. So questions will be answered throughout the presentation, and then at the end, we'll have some question and answer that's live where I can answer things for the audience. Okay, so the first thing I wanted to cover is what WaveFarer is. So high fidelity radar simulator that accounts for scattering from complex geometries, including vehicles, structures, and people. WaveFarer includes multipath with the environment, and this can be used for automotive radar, where it's interacting with buildings, roads, walls, or in an indoor case, it can be interacting with walls, floors, diffracting through doorways and furniture. Atmospheric absorption was a key thing that has been added to allow us to go up into the millimeter waves, and this becomes very important as we get up above X-band frequencies. The uses for WaveFarer include predicting radar backscatter from objects in an environment, similar like the scene shown here. And it can also be used for analyzing far-field radar cross-section of detailed structures, such as aircraft or vehicles. The key methods that are used by WaveFarer, it's a ray tracing-based solver, and it uses key physics methods of physical optics for the backscatter. This involves a surface integration that can predict detailed backscatter from highly faceted objects like vehicles or people. Unlike a lot of traditional uses of physical optics, this implementation does not make far-field assumptions, and that allows us to include spherical wave incidents and very close range kinds of applications of a few meters to tens of meters, rather than being limited to far zone RCS. We augment this with method of equivalent currents, which adds edge effects, and similar to diffractions, allows you to handle the effects that happen at edges through a line integration that's very compatible with the physical optics integration. And then this is combined with geometric optics and uniform theory of diffraction, calculations that are used to propagate through a scene, to reflect from surfaces, diffract around corners, and interact with elements of the environment around the target geometry that we're scattering from. The ray tracing methods are based around a starting point of shooting and balancing rays, Shooting and bouncing rays can find all the paths from a transmitter to a receiver by bouncing through the environment. And this gives us our first start at the ray tracing as we see where the paths and waves propagate through an environment. However, we have a lot of unique enhancements over shooting and bouncing rays that are very critical for the radar scattering. One of them is targeted raycasting. So when we're doing our surface integration, we need to make sure that we are illuminating all of the facets of our target geometry. And so targeted raycasting makes sure that when we ray trace, we hit all of the facets, and we've combined this with multipath so that our multipaths are also illuminating the entire vehicle so that we can do an accurate surface integration. A second enhancement is exact path correction. So shooting and bouncing rays can show you where rays propagate through a scene, and it gives you, to within some level of accuracy, it gives you some idea of where the waves are propagated. But when you get down to an individual point where you're doing a surface integration, or when you capture that with a receiver, to get the most accurate calculation, you need to have the exact path that goes from this precise transmitter point to the precise receiver point, interacting with all the different surfaces along the way. And our exact path correction uses additional techniques based on image theory to do just that, to make sure that the final paths that we're using in our calculations are precise and go from the specific transmitter point to receiver point. This is not only important for something like a surface integration for scattering, where phases are absolutely critical on each of the facets that we're interacting with, but also if we have an array and we need to know as we move across the array how the phase and polarization shifts. Another key element is that multipath from all of these interactions is captured on the way to our target as well as on the way back. And this ensures that reciprocity is maintained in our calculations to the extent possible. Okay. So applying radar interactions within an environment, the key characteristics of radar include the frequencies, and a lot of times in the scene scenarios that we're involving, we have higher frequencies like X-band and millimeter waves, antenna radiation patterns, possibly pulsed or chirped waveforms. And as we interact with the environment, one of the big changes that we see when we go from a far zone technique, which might use radar cross-section and a range equation, in that type of a technique, if you were trying to apply it to a range, you might see a smooth fall off as you move away in range. When you integrate this with reflections, however, you get a lot of near zone effects and a lot of effects that happen with the environment. From the ray tracing, we can pick up ground bounces, we can pick up interactions with other objects. And so instead of a smooth fall off as we move away from a scattering vehicle, we may see a pattern that looks like this red line where we get fading and a lot of interference effects from all of the things in the environment. This is what we can pick up with the WaveFarer simulations and the ray tracing that we've integrated. When we're talking about drive scenarios, this can include clutter from things like guardrails, street signs, maybe buildings, walls, and poles. The basic starting point for the responses that we capture from our radar scattering are the complex impulse response, which gives us the magnitude, phase, and time of arrival of each arriving path that is propagated through our scene. And on the bottom here, we can see that if we were to simulate just a car in an environment and we ignore all of the multipath, we might get a backscatter. Even if a very detailed backscatter would look like this red set of returns here. When we fold that into the environment, we get ground bounce effects that maybe increase or reduce the scattering from the car itself. And then, of course, we see a lot of additional returns that are coming back. In this case, it's from corner reflector effects that we see in each of these guardrail posts. And of course, a reflection from this sign. So all of these different elements combine together to give us the total view of what's going on in the scene and how fields are propagating and scattering. Now, when we look at an indoor scene, the interactions are a little bit different. We have a lot of interactions with walls, furniture. We could be scattering on things, diffracting through doorways, and even transmitting through a wall. So in this indoor case where we have a sensor in the corner that's going to view a person. We can see that the paths travel in a variety of different directions that include transmission, scattering from surfaces, and a variety of other types of propagation. So it's a little bit of a different environment. The overall types of interactions are the same, but the geometry is different, and it leads to some different kinds of interactions and scattering. So in WaveFarer 2.1, we added some new features, and we're going to be highlighting some of these throughout our demonstration. One of them is diffuse scattering. This captures clutter from rough surfaces on roads, walls, and other structures. We have multiple models that are tunable, as we'll describe a little later. And one of the things that's critical to be able to use the diffuse scattering with the Doppler calculation is that we've spent quite a bit of time developing and implementing these methods with some extensions that allow us to retain relative phases between pulses. So when we're dealing with a diffuse scattering calculation, the phase, it's not possible to know the phase because we're interacting with things that are much smaller than a wavelength in these models. So the phase is randomized, but the integration points and the initial phases are retained between the pulses. So we are able to capture how those phases may shift relatively as things are moving over very small distances, such as the frame for a sequence of chirps. And this allows us to capture a Doppler from the scattering. The scattering aggregates paths over each facet. So we have the option to break up something like this asphalt into lots of small facets so that we can capture individual ray paths. And in this view, we can see a lot of small ray paths here that are going out to the asphalt that are due to diffuse scattering, and that's being added in with some of the more specular scattering returns that we get from the car, the guardrails, and the sign. Overall, what we tend to see is our complex impulse response shown in blue. When we add in diffuse scattering, we see a great deal of additional clutter, particularly at closer ranges where the power is strong. And this adds more of the interactions that we're going to see as we're driving in an open roadway scene. So a little bit more about our diffuse scattering models. There are 3 different models that we can choose from. One is a general scattering method called the Lambertian method that scatters uniformly from a surface. And then we've added a directive method developed by Degli Esposti and a directive with Backscatter. These are 2 methods that were developed primarily intended for ray tracing and in large part for interactions with buildings and building scattering. So we have these available as well. And in those cases, rather than scattering normal to the surface, the scattering creates a pattern that centers about the normal specular reflection or the backscatter direction, but spreads out from that direction according to some other parameters. So these parameters are tunable, and there is some literature available that we can use to set the values, and we've done so for our demonstrations. And one last item is the cross-polarization factor. The nature of diffuse scattering is that it can add a lot of cross-pole power into the scattering, and so there's a cross-polarization factor that can also be set that allows the backscatter to have some polarization that is perpendicular to the normal scattering directions. So another new feature is transmissions through materials. So in this case that we show here, we show some rays that are transmitting through walls. So without the transmissions, the main propagation paths might diffract through a doorway or reflect off an opposing surface, but we can now also capture the transmissions through the walls and combine that with scattering from an object within the scene. We also can transmit through a window and interact with the interior of a vehicle. So we could pick up interactions with passengers or with seat backs or other things that are inside that might also affect the backscatter. In addition to transmissions, we've added some new materials. These include a perfect absorber, the ability to define magnetic material properties, to define multi-layer dielectrics, and then we also now have an ability to include tabulated dielectrics, which we'll show a little bit later. And that allows us to have a database of properties that can vary all the way from 100 megahertz up to 100 gigahertz, so that you can define a material and have it choose the appropriate sets of values based on the frequency where you're operating. So the scripts, WaveFarer comes with a very thorough scripting capability that allows you to augment the normal calculations with your own post-processing or pre-processing. And with this release, we have included several different scripts. Some of them are packaged with the release to include a script that allows us to do some path viewing using a path viewer based on another product called XGTD. This is bundled in with our script and can be executed from within the graphical interface. And then we also have a series of scripts for range-Doppler calculations. This package of scripts can set up the simulation for a series of chirps for Doppler. It can execute them. And then we have a second set of scripts that can post-process them to do range-Doppler and also generate some other outputs like the I and Q or S parameters. So we're going to demonstrate these range-Doppler calculations a little bit later when we do our demonstrations for our two scenarios. We also have some additional outputs such as RMS angle spreads, delay spreads, power as a function of angle of arrival shown here, and of course the propagation path outputs. A little bit later we'll show some uses for the angle of arrival plots as well. So in calculating and simulating chirp waveforms, the first set of scripts that we have sets up a series of chirps in terms of frames. So a chirp may look like this diagram shown here. Our script generates a sawtooth chirp. The user can configure parameters for the lower frequency, the upper frequency, the duration of the chirp, the reset time between chirps, and the number of chirps that are in a frame. The script will then set up the simulations, apply the appropriate frequencies, perform calculations and generate results, and package all of this in a way that can then be used by a second set of scripts that can post-process and do range-Doppler calculations. A key optimization that we have included is that we are able to export out detailed path data and map paths between different chirps. And we have used this to apply some significant optimizations that allow us to adjust the phases of those paths mapped between the chirps at the ends of the frame. And with this level of information, we can adjust tens of thousands of paths between the chirps at either end of a frame and capture the processing needed for that frame with just two simulations within WaveFarer. This is very significant. If we have 256 chirps, for example, gives us a couple of orders of magnitude speed reduction in being able to simulate a frame. And then we can simulate several different frames to give us snapshots of what happens within a scenario. And we'll demonstrate this a little bit later in this webinar. So the range-Doppler post-processing extracts detailed path data, adjusts those paths based on distance, magnitude, phase, and of course the frequency of the transmission. It calculates I and Q at a series of sample points, and then it uses fast Fourier transform processing to generate range-Doppler plots. Optionally, you can export the impulse response, the S parameters, and the I and Q data. Some of the key assumptions for this are that the motion during a frame is fairly short, and that's typically true for the scenarios that we'll show. Basically, the start and end of a frame are happening over a few milliseconds, so objects in the scene are not moved very far. The paths are generally the same, but they are shifting, and these are some things that allow us to apply our optimizations. And a second one is that frequency dispersion. We make the assumption that this is driven primarily due to the path length, and that we can adjust the paths according to their frequencies and their distance traveled. And doing this with tens of thousands of paths allows us to capture the phase shifts so that we can do our Doppler calculations. So we perform a series of Fourier transforms, starting with a transform on the mixed down signal of the I and Q, and this allows us to determine the power versus frequency, which we show in this plot here. This is done on a single chirp, and this plot is from a single chirp. This is performed on each of the chirps in a sequence of chirps within a frame. Once we have this result for a sequence of chirps, we can do a second DFT across the chirps, and that gives us the range-Doppler and generates a plot as like the one shown here. So in an example similar to the one we showed earlier, we have a car that's 23 meters or so out in front of the radar, and we have a series of guardrails, and they're showing up with a Doppler that is equivalent to the speed of the radar, in this case maybe 20 meters per second. And as the radar starts to pass the guardrails, they start to shift and eventually would show a negative Doppler if they're picking up scattering from behind the vehicle, depending on the beam pattern. So we'll start with our demos now. Our first demo is an automotive radar with a car crossing at an intersection. So we start with a 2-lane highway with a side road. There's a car at a stop sign. And during this scenario, the car will accelerate to cross over the highway as a truck moves by and a car approaches. In this simulation, we have simulated a series of intervals, 1 second apart, a series of snapshots. Our truck is moving 15 meters per second. Our radar vehicle is advancing at 15 meters per second in the opposite direction. And our car is stopped at the sign in the beginning of the simulation. After the truck passes, it begins to accelerate at a rate of 4 meters per second squared and crosses in front of our radar. So one of the scripts that we have within the WaveFarer suite allows us to sweep the positions during time. We've set up a series of parameters that define where everything is during the scenario. And we can now sweep from 1 to 5 seconds. And this plays what's going to happen in the simulations and the results that we show later. So we'll just show that one more time. So the car is advancing after the truck passes. This car crosses in front. We have selected to do a series of snapshots, 6 different snapshots throughout that scenario, and we'll do a frame to do Doppler processing for each one. Now in our geometry, you see asphalt for the roadway, you see the terrain, there's a stop sign with a pole. We of course have the truck, the car, and we have the radar and some guardrails down here. Each of these colors that you see is a different material. And if we want to look at the asphalt, for example, we have some values from literature, a real and complex permittivity that we have has been set, and this is used for the asphalt. The dry ground, we have some parameters from an ITU recommendation. And so we have those defined as the permittivity and the conductivity defined as a function of frequency, all the way from 100 megahertz up to 100 gigahertz. And likewise, for each of the materials in these cars and trucks, we have properties as well. For example, we see another IT recommendation was used to feed the properties for the glass, for the window in the car. And so on. We've got plastic, we have rubber for the tires. Each of these different things has been defined in terms of separate materials. Now in this case, our radar sensor has been defined as a transmitter and a receiver about a wavelength apart. If we zoom in, we can see these placed here. Green is the transmitter, red is the receiver. And so in our simulation, those will be advancing along with the vehicle, and that will control its position. We can also do arrays if we would like to, and we'll actually show an example with an array for the indoor scenario in a little while later in the next demonstration. Another thing that we saw there was the antenna pattern. In this case, we are using an antenna pattern that was generated through simulations with a full wave solver, XFTTD. This used a geometry to try to capture the detailed patterns of side lobes due to interactions with the structure of the front of a car. And so we have pulled this pattern in to give us a little higher level of detailed fidelity for our simulation. So overall, we have an EIRP of about 25 dBmi. Our frequency is going to be around 77 gigahertz. We have a 540 megahertz bandwidth, and we've basically specified some nominal parameters for a mid-range radar. Down below, we show some of the chirp parameters. We have a sawtooth. Our chirps are about 27 microseconds apart. We have a series of chirp frames, sampling rates. So these are all properties that we can now set within our scripts. As an example of how this is done, if we want to create a linear chirp simulation, we actually can just go up to our macro here. This is a script that can be downloaded from our support site. And when we run the script, we just fill out our properties here. We can define how many frames that we would like to simulate. And since these frames are being used for instantaneous snapshots throughout the scenario, we can space them apart as far as we want. We don't have to simulate every frame. Each frame is its own contained result. We can set the start and stop frequency for our chirp, the length, reset time, number of chirps, And then we can choose if we want to save the simulation to run later, if we want to queue it and run it now. Once the simulation is completed, we can review some of the outputs. So the standard output from any simulation is a complex impulse response. And this gives us magnitudes, phases, and times of arrival for all of the contributions that are coming from various things in our scene. As we move through the different seconds of the simulation, you'll see these moving to the left as the radar is closing on the truck and the car in front appears. It's difficult visually to see all of the details from this, but once we start processing this for range-Doppler calculations, we can see a lot more. Now, if we want to get a little bit of a view, another option is to take this same impulse response and view it in terms of angle. So at the starting point, this is a plot that shows us an impulse response that has been aggregated into azimuths of arrival. And we can see a series of responses over to the right here. These are coming from the guardrails primarily. On the left, we're getting interactions from the truck and maybe from the car. As we advance, the truck gets a little closer, the guardrails start to pass. And at this point, with the truck passing, the ranges of angles change quite dramatically as the truck is now driving past our vehicle, and we're starting to pass the guardrails as well as we're approaching the intersection. And now as the truck has passed, we start to pick up the car, and then the car crosses in front of the radar and we see it swing around to the right. So that's another one of the outputs that we can look at. Returning to our chirp and our Doppler calculations, now that we have the simulation performed, that script is going to kick off a series of simulations that capture all the information we need for those 6 snapshots. In total, there'll be results from 12 different simulations capturing those 6 frames. So our first frame was at 0 seconds into the simulation. This is the relative position of where everything was. We get our Doppler calculation produces a plot of the Doppler versus time. We can see interactions with guardrails, the truck, and the car over here in the distance. When we do the Doppler processing, we pick up this scattering plot. The range-Doppler plot here shows over here is the truck. And then at the moment, the car is stationary, and this is most likely the scattering coming back from the vehicle at the intersection. As the radar advances, the truck is getting closer. And of course, we see some of those guardrails are approaching and then passing and shifting down in Doppler as they pass. The truck is now again getting closer. Its return is stronger. And we still have the car stopped over here at the stop sign, although it's partly obscured by the passing truck. Now the car starts to move out, and we're getting a little bit of a relative velocity here based on this angle as the car is driving. But primarily its velocity out in front is at about 15 meters per second here, the speed of our radar. And our truck again is passing by here, it's much closer. And now we see the car out in front, again getting our 15 meter per second velocity. And now as the car has passed, it's now getting a negative velocity because now relative to the radar, it's moving away. So all of this is done in our post-processing. Next, we thought we'd add in some diffuse scattering for the road. So based on some measurements and some different values that were available in the literature, we chose scattering factor of 0.4, actually matches up with our defaults, and we applied this to both the road and the terrain. Now, if we wanted to look in our path viewer and compare these two cases, here's the case that we just looked at. We didn't have diffuse scattering yet. And this is just looking at the top 2,500 paths or so. Now in the diffuse scattering case, when we do the same thing and look at the top 2,500 paths, we see a whole lot of additional interactions, particularly in close. And again, this is just the top 2,500 paths. In our Doppler calculations, we're actually keeping the top 20,000. And we can go up to 100,000 in WaveFarer if we want to look at large numbers of paths from the scene. So as you go up to higher and higher numbers, lower down in power, you'd see these spread out. There's actually a lot of things contributing that are going much farther out. But these are the strongest paths that are being seen. So these two things are the difference that we're going to see, and that's what's leading to this additional clutter, especially in close. So now when we repeat this at the 0-second point, but now with the diffuse scattering case, you can see we've got a lot of additional clutter now coming into the range-Doppler plot. We still have the truck out here. And as the truck is approaching, it gets closer. There's a lot more clutter. There is some interesting multipath happening here. The truck passes. And of course, we see the car emerging from behind the truck out in front. And very strong signature now as it's directly in front of our vehicle. And then as it moves away, it's now passing in here through this field of clutter. So now if we move to an indoor millimeter wave sensor, we've set up an example that's meant to simulate perhaps a people counting and tracking sensor. Might be used for a safety application or to control a thermostat of the lights. There are a variety of different applications, some for medical, some for other purposes where there are sensors being placed inside that can detect the presence of a person and perhaps some type of motion. So we've simulated one of these. We've set an operating frequency at 60 gigahertz based on some systems that are available now out in the industry. Field of view of about 120 degrees. And we mounted it up in the corner facing the entry doorway, which would also be pretty typical of this type of a sensor. Now in this simulation, we have the person entering the room and moving at a walking speed of about 1.4 meters per second starting here and moving into the room. And in this case, we've calculated the range Doppler this time for 5 snapshots as the person moves from this position to a position further into the room. If we repeat our time sweep, we can this is the range of positions that we'll cover. So we start with the person outside the room on the other side of the wall where transmissions may come into play. And then as they move through, we'll see a lot of multipath from the walls and the furniture in the room. In this scenario, there are certain settings that we use in WaveFarer to define the environment. And those can be things like the walls, the floors, the road, the terrain. And there's a setting for things that we want to capture detailed scattering from, and that invokes the additional approach that does the targeted ray shooting and makes sure that all the facets get hit. So in this particular scene, we marked the projector screen stand as a scattering object. We've got a small projector here on the table, and also some chairs within the scene that are all defined to produce scattering. And of course, we have the person as the person is entering. So running our simulations, one of the results that we can get from the scenario is the paths. So this is an example of some of the multipath that we can see. So we can see clearly that there are transmissions, including some transmissions that come across the room and then interact from behind. And of course, in this first part of the scenario, the strongest paths are going to be things that are interacting with things such as the walls on the opposite sides, where there's a strong reflection coming right back to our transmitter. But what we would hope is that the sensor has some Doppler processing that'll help it to pick up the motion of the person, and that may help it to pick that out of all of the clutter and all of the strong returns that we're seeing from other things in the room. So next for this setup, we also set up a chirp waveform and did some Doppler processing. So in this case, we set the bandwidth to operate in the 60 gigahertz band, somewhere in the middle between 60 and 64. We set up a sawtooth and set up some different chirp parameters and sampling parameters. And they essentially give us the range resolution and the Doppler velocity resolution shown over here. So one of the things that our scripts provide is they will tell you as you fill in these parameters to do your processing what the extents will be, the resolution, and the range. So in this case, we have a max range of about 18 meters for this calculation. We've seen things in the literature that go from maybe 6 to 15 or so. So it's on the order of that type of a thing. And and you can then configure those. And so we've used some rules of thumb from some sort of nominal design parameters that could be configured, and we've configured them for our particular room setup. So as we go through the results then, our first case, at 0 seconds, the person is on the other side of the room. Here's what our range Doppler looks like. We can see with the person moving, relative to the radar, we're getting maybe a 1 meter per second Doppler. We can actually pick up the person on the other side of the wall here. But we do see some strong returns coming in at 0 Doppler, stationary, from different parts of the room. We've looked at these distances and identified the likely culprits. The farthest is this far corner. There's a corner reflection. We have interactions with the far walls here, and there's some interactions over here with this alcove that are coming back. And so that's what we're seeing in the strong Doppler. But if we pay attention to here about the 1 meter per second distance, we can follow what's going on with this person. And we've circled this to make it a little easier as we move along. So as the person moves to the doorway, we can see that their signature gets stronger. We've also got them circled here. We can now start to see them even in the power versus range plot. But we clearly picked them out here based on their motion. And as the person moves through the room, an interesting thing starts to happen as they get toward the middle of the room. We start to see more and more multipath, both at the 1 meter per second or so, some a little faster, but also in the opposite direction. And this Doppler you could attribute to probably some reflections happening off the wall and hitting the person from behind. So they're moving away from that reflection of the sensor. And then in our last case at the bottom of the table, we can see where their signature is, and we can also see some multipath effects. So these two demonstrations have covered what we have in the scripts that we are distributing on our support sites, and the path viewing script, of course, it's distributed with our software. But we thought for this example, we would take this one step further and develop some additional code in MATLAB that could analyze our results and do a third FFT to do some angle estimation as the person's moving through the room. So in this case, we simulated 4 receiving sensors and 3 transmitters, and we spaced them apart in a way that would allow us to apply them as 12 virtual sensors. And with those 12 virtual sensors, we could then use those 12 returns, the 12 different angular variations across that virtual array to do some angle estimation of where the person was as they were moving through the room. So we applied a third FFT now, taking the peaks from the range Doppler at each range and plotting the results in a range angle map. Now in this first case behind the wall, it's difficult in our angle estimation to make out the person just yet. But as we get to the next position and they start to enter the room, you can clearly see them. And these angles are relative to the pointing direction of this sensor, which is pointing toward the middle of the doorway. So the person is just to the right. And you can see as they move in front of the antenna and start sweeping across the room toward the left, that we can position them using our angle estimation techniques. And of course, you'll see this throughout a lot of these plots, but these 2 points here show some very strong multipath. And some of these are probably coming from, again, from reflections from other directions hitting the person from various directions that make them appear to be at different angles. Perhaps a reflection off the wall gives an apparent direction toward the right. And so these are all being combined into these estimations to see what the radar would see in this situation. So that concludes our 2 demonstrations. The goal of the webinar was to demonstrate some of these new features that have been released in WaveFarer 2.1. We showed 2 different demonstrations, the auto radar intersection scenario with a car crossing and accelerating out in front of our radar, and an indoor mmWave sensor scenario for people counting. We've shown also how the range Doppler scripts can be used to do some calculations and then done some additional calculations in MATLAB on our own to show some angle finding. So our goal was to show how these new features can be used in analysis, and we hope that you found this useful, and we thank you for attending. So now we'll take some questions. While I'm taking the questions, I'll leave this up. If you have any further questions about this, feel free to reach out to the sales email shown here. And please note also, there are questions coming in. We probably won't get to all of them. So if we don't get to your question today, rest assured that there will be members of our technical support team that will reach out to provide answers one-on-one afterwards. Okay, so one of the questions was how the phase affects the simulation results. And this was early on in the presentation, probably as we went through the Doppler, this might or might not have been clear. But the key element, so the starting point for everything is the complex impulse response with magnitude, phase, and time of arrival. The phase is a key part of that, and that phase also then gets further adjusted through the post-processing scripts to account for all the frequency shifts that are occurring for the chirp waveform. That phase then is critical to the Doppler calculations. The Doppler calculations across several chirps are applied, and the phase is the key element that helps, that leads to the Doppler calculation determining the relative velocities based on how those phases shift between chirps. There's another question about the shooting and bouncing ray technique and the electrical size of objects. And the question was whether or not, since we're using the shooting and bouncing ray technique, do we assume that our objects are electrically large? So the electrically large condition tends to be one that is applied to the EM physics techniques, the uniform theory of diffraction, the geometric optics that's doing the reflections. And so we talked about how we break up our scene and we define things that are part of the environment, the terrain, the buildings, those things that we, perhaps in the floor plan, the rooms, the walls, and the floors, those are things that we define as part of the environment, and they're treated using those techniques that assume that the parts of the environment that are being interacted with are going to be large compared to a wavelength. Now, a couple of things are important here. One is that the wavelengths in these simulations are very small, so that electrical size can still be applied to a lot of the scenes that we showed. But then the second important thing to realize is that we use physical optics as well. We do a full surface integration, and the physical optics does not have the same constraints. So while we're using the shooting bouncing ray technique to try to determine where paths go, when we get to the physical optics, we are doing a full surface integration down at very tiny facet levels, at perhaps facet sizes of a few centimeters. So those same constraints do not apply, and we're able, with the physical optics technique, to get accurate radar backscatter from very finely detailed surfaces. Thank you for that question. There's a question about the slides and whether they'll be available. And yes, they will. We will be posting a recording of the webinar soon, and when it's available, all attendees will receive an email from Remcom with a link that allows you to download those slides. There were some questions about runtime, and so the simulations vary quite a bit. For the automotive radar simulation, so the question was how long these simulations take. So using these optimizations for the chirp simulations, the automotive radar case took a couple of minutes for each simulation that was bounding the frames. So for a frame, you might expect it to take 3 to 6 minutes for the first case, perhaps about 6 minutes in this case with the truck and the other car. So we had a series of 6 frames, and so if they were all run individually, depending on your resources, that might take anywhere from tens of minutes to an hour. When we added the diffuse scattering, that increased the runtime, in part because we also increased facetization so that we could pick up the detailed paths for our path displays. So there's some options there as well, but that could double the runtime. The indoor case took quite a bit longer because it did have a lot of interactions within the room. So, and in that case, in one of the instances, of course, we were also doing the array processing. So that's going to depend a lot on the geometry and the number of structures that we put. But in this case, it took a few hours for each frame to complete the frames, and a little bit longer when we did the array processing. So, and this is just in part because of the vast number of rays. There were billions of rays that were found in paths that had to be analyzed to determine all the strongest paths. So it's quite an interesting scenario in terms of the amount of ray paths that are generated. And that was another case, of course, where we did several frames. Each frame requires 2 simulations. So let's see, there's a question about timber structures and whether we can see through them. And the transmissions that we show can go through any material that transmissions can go through, which is pretty much any material unless it's one of our ideal materials. So a perfect absorber or a perfect electrical conductor, or of course, effectively, if you set dielectric properties for something to be metallic, then there won't be much going through it, if anything. And if it's one of the specialized one, no paths will go through. But if you set it to wood or sheetrock, like our walls, then rays will absolutely go through the wood. So you specify the thickness, the material properties, and it will estimate how much transmits through the material. And with the scattering calculations, if we transmit through, we may then interact with something on the other side and then transmit back to the radar. There's a question about a couple of questions, I guess, related to frequencies. So we tend to quote the frequency range for WaveFarer is going from 100 megahertz up to 100 gigahertz. That's a nominal range, and the reason we quote that is there's not a hard fast limit. Below 100 megahertz, if you go enough below, you might start to run into certain phenomena like surface waves or other things. And above 100 gigahertz, maybe you'll see some the scattering becomes more intense. And we do have some simulation experience going up a little bit above 100 gigahertz. We just tend to set that as our upper bound for our ray tracing products right now because we know that there's more research we need to do to try to make sure we understand how best to model the small features and the scattering from them that's going to be more and more important as you go up to high frequencies. So some of that might be, just facetization. What level of detail are you going to have to include in your simulation? And some of it might be the models, whether we might need to add some new models to continue to extend our ranges. The atmospheric absorption that we mentioned goes all the way up to 1,000 gigahertz, so that's not limited at all. So it's really, like I said, it's a rule of thumb. It's not a hard fast limit, and we expect to be continuing to push that up as we get more confident in the techniques that we want to use. Okay, well, I think that's all the time that we have today. I want to thank everybody for attending and for your lively questions. Really appreciate that. Um, As I mentioned earlier, we'll be posting a recording of the webinar soon. Once it's available, you should all receive a link in an email from us to download the recording. And anybody whose questions we didn't get to today, I know there were a lot of questions and I don't think I quite got to all of them, but we will reach out to make sure that we get back to the rest of you and we'll follow up one-on-one. So thank you all again, and please enjoy the rest of your day.